meters per second.
So that's how fast we're traveling, assuming that the center of the Earth is not moving. That's how fast we're traveling. And so, in a day, the satellite's off by 9.5 microseconds. So how far do we actually travel in that amount of time? So 463.97 meters per second times 9.5 times 10 to the negative 6th seconds. I guess that's seconds per day. Why are we getting different numbers than that?
4.41 times 10 to the negative third to the negative 3 meters per second.
It'd actually be meters per day.
Per day. Oh, right.
So every day, it's almost 4.5 millimeters. The satellite would be off. Okay, still doesn't seem like a whole lot. But if we multiply by 365 for an entire year, then we're now starting to look into a meter a year, and ish.
About 1.6.
1.6, which translates to approximately 1.6 meters per year. And so that you can see that over time, these things will get farther and farther off. Now, to complicate matters, you also have to take into account general relativity, but that is beyond the scope of my abilities. So, GPS satellites take this into account. Let's see, there's another topic I missed. Questions up to here?
No, I'm okay.
That's 1.6 meters per
Year.
year.
Alright, so simultaneity. Apparently. And so the lower place, so after that, oh, that's why. Alright, we did simultaneity, yes, DART, 2 days ago. There we go, that's what I want. So now, hole in the barn. Then skip ahead just a little bit to, we had left with also that in the prime frame is equal to gamma x minus vt. I think that was written up on the board. So this would be, we did the example of if you're in a car at a stoplight and then someone's on the side of the road, if the car starts moving from the car's point of view, that would be the distance to the next light. And from the person on the side's point of view, back that up. From the car's point of view, that's the distance to the next light. From the person on the side of the road, that's the distance to the next light. relativity, gamma gets thrown in. And then the other relating time is equal to gamma time minus bx over c squared. I derived neither of these, I just presented them as if it's obvious. Make sure I did not write it down wrong, bx over, yeah, that's right. I'm going to change the number slightly. Into what hopefully will be easier numbers to work with. So from the barn point of view, I have a pole that is moving towards the barn at beta is equal to 0.866. I think yesterday I did 0.8, doing 0.866. The width of the barn is 10 meters. And I'm going to set this up so that it won't hit the roof of the barn. Get it all. There we go. So we are measuring position from the pole's point of view from the left end. So this is where x prime equals 0. And we are measuring where things are from the barn's point of view from the left. There's a door here, the left door. We're going to synchronize our clocks, so when x prime is equal to x equals to 0, in other words, when the left end of the pole just makes it into the barn, that's when we synchronize the clocks. That's when t prime equals t equals 0 seconds. Now, from the barn's point of view, the pole was traveling near the speed of light, and the pole will be shorter. I know that the length of the pole, the proper length of the pole is equal to gamma times the length measured. Proper length of the pole, I'm going to keep that the same as before, 16 meters. So that P is for proper, not pole. Let's go ahead and establish the proper length of the pole is 16 meters, and the proper length of the barn, or technically width, is 10 meters. That's going to be equal to gamma times L, and I'm trying to figure out L, so L is going to be that divided by gamma. Well, gamma, 1 over the square root of 1 minus beta squared, which is 1 over the square root of 1 minus 0.866 squared. And what do we get for gamma? That doesn't sound right.
I got 1.999.
Yeah, it should come out somewhere close to 2.
Okay, let me try.
I picked 0.866 so that it would come out close to 2. You getting the same thing?
Yes, I got this.
Yeah, 1.999?
No, I
you
still
got
got
1
my same. Oh, I did.
Ah,
I see. Now.
okay.
Sorry. I multiplied it instead of subtracting.
Ah. So the length, from the barn's point of view, The length of the pole would be 16 meters divided by 2, which is 8 meters. So from the barn's point of view, when the left end is inside here, the pole is going to be shorter. It's going to be 8 meters. In the barn, from its own point of view, it's 10 meters. As soon as the left end, as soon as we synchronize the watches or the clocks in the barn, both the right door and the left door will immediately close. And then the pole is going to smash into the right door. So we have 3 events here. We have, so this is the barn's point of view, barn point of view. We have event 1, the left door closes. Event 2, the right door closes. And event 3, actually, the 3 events are happening in either point of view. Event 3 is pole hits the right door. Now here's the barn point of view. I'm going to express this in terms of x and t. So the left door closes at 0 meters, 0 seconds. So from the barn's point of view, that's the origin from the barn. That's where the left door is, so that's why that's 0 meters. And it closes as soon as the left end of the pole gets inside, which happens at when we synchronize the clocks to be 0. The right door closes, well, the position of the right door would be 10 meters, and it closes at the same time as the left door does from the barn's point of view. And then the pole's going to hit the right door, well, that's at 10 meters because that's where the right door is, but the time we do need to calculate. So from the barn's point of view, how far does the right end of the pole need to go to hit the door? It's not a trick question.
Saying how far it needs to go 10 meters.
At the moment that time is equal to 0, the left end has just gotten inside. How far does the right end of the pole need to go before it hits the door? Before it hits the right door?
I know it's not a trick question, but I don't know.
Okay. Benon?
Yeah, what do you think?
You said that's happening at 0 seconds?
This at 0 seconds, barn's point of view, 0 seconds, this is the scenario. Okay. The fact that there's not an immediate answer tells me there's a disconnect somewhere.
Yeah.
All right, so your table is the barn.
Okay.
It is 10 meters wide.
Right.
You have a pole that, if it were at rest, it would look like it's 16 meters, but it's not at rest. It's traveling really fast, close to the speed of light. So it actually, from your point of view, is 8 meters long. We will pretend that this is 8 meters long. So from your point of view, it's coming at you when as soon as it clears the left end, the left door and the right door close. Again, this is 8 meters long. Your barn is 10 meters wide. How much distance is there before this end hits the right door? Yes.
I was thinking that, but I was overthinking that I would probably wrong. So I don't wanna say
Overthinking
it.
relativity? What?
I don't want to say it. It looks stupid.
So the question is, from the barn's point of view, how long does it take? Because I need to figure out the time it happens. How long does it take for that right end of the pole to travel 2 meters? Well, I know that speed is distance over time. I'm trying to find time, so time would be distance over speed. and that's 2 meters, divided by 0.866 times the speed of light, which is about 3 times 10 to the 8th meters per second. That's meters.
I guess 7.698 times 10 to the negative 9.
Units?
Seconds.
And so 7.698 nanoseconds. Not a whole lot of time, but then again, you have something traveling near the speed of light. It doesn't really take long to go 2 meters. Actually, if it's traveling the speed of light, how far does light travel in a nanosecond? Just give some sort of relative, give some sort of, I guess, physical sense to it. So I want to know how far it travels, so the distance is the speed times the time, so 3 times 10 to the 8th in a nanosecond, 10 to the negative 9th. And so in 1 nanosecond, light will travel 0.3 meters. So in 1 nanosecond, light travels how far? If you need it quick and dirty, yeah, that's slightly more, but light will travel that far in a nanosecond. All right, so we now know what the time will be. So 7.698 nanoseconds. All right, any questions from the Barnes point of view, how we got those position time coordinates? All right, so now let us figure out what is it from the pole's point of view. Because from the pole's point of view, the barn is rushing towards it. So from the pole point of view, we have the pole. Well, the pole is 16 meters long, and the barn is rushing towards it with a width of 5 meters. And beta equal to 0.866, which gives us a gamma of 2. Which is why it's 5. It's the 10 meters, the rest length of 10 meters divided by gamma. That's how we got 5 meters. So when the left end clears, so when the left side of the barn gets to this point right here, I got my 5 meter barn, and I have a whole lot of poles still sticking out. Well, let's do a quick plug and chug. Define the position. So this is barn. That's probably where I should have written barn. Barn. And then pole. X prime, T prime. So I'm going to take my 2 Lorentz equations over there and just plug this in. So X prime for the event number 1 is 2, that's my gamma, 0 minus 0.866c times 0, which is my time. And hopefully you'll notice that that's 0. And that makes sense. 0 meters, because that's when the origin of the coordinate system of the pole is the same as the origin of the coordinate system of the barn, yeah, they're both 0. To get time, I have 2 times time, which is 0, minus the speed of light, 0.866, times the speed of light, times the position, 0, over speed of light squared, and you'll see that that's 0 also. And that again makes sense, just because we established that when the 0 meters for the pole and the 0 meters for the barn match up, we synchronize the times at 0. So that matches basically what was said in the problem. Now the next part. Things will start to get a little bit stranger. So for event 2, x prime is equal to 2, that's still my gamma. And then my position is 10 minus, look in the wrong spot, 0.866 times the speed of light times time, which is 0. So I get 20. So the right door is going to close when it is 20 meters away from the left end of the pole. The time has got to be negative. So T prime is equal to, again we have 2, the time is 0 minus Vx, so that is 0.866 times the speed of light, 3 times 10 to the 8, times x, which is 10, divided by 3 times 10 to the 8 squared. That's going to cancel out with one of those.